In this video, we're going to explore the concept of potential stability. We begin by considering the last two terms of the Lapse rate equation, which examine stability changes by vertical motion, and these two terms can be combined into one. Consider then a layer of atmosphere that's lifted and stretched by vertical motion. On the right hand side we can see what happens to a layer that's where the bottom and the top of the layer are lifted at the dry adiabatic lapse rate. And you can see as the parcels rise that the top of the layer lifts more than the bottom of the layer, and we tilt the lapse rate. So we go from a stable environment to a less stable environment. Likewise, if you descend from A dash B dash, then the environment becomes more stable. As an exercise, plot the following layer of atmosphere and calculate the theta dz for the layer in degrees Celsius per kilometre, consulting the IKO scale. Then lift the bottom and the top of the layer by 200 hectopascals and recalculate the theta dz. What has happened? I'll plot it on here, pause the video, and then we'll discuss it. So, what did you find? These are our starting conditions, and we can approximate the theta dz by simply the difference between theta at top and bottom of the layer divided by the depth. Initially the depth is 800 meters, and then as we lift the layer, the depth of the layer becomes 1000 meters. And so, once we've done that, we find that before lifting, the answer is 12.5 degrees Celsius per kilometre, and after lifting, it's 10 degrees Celsius per kilometre. So there's been a change in the lapse rate. Note that the difference in pressure between the top and the bottom has not changed, it's constant, but the difference in height has. So in other words, omega, which is the p dt, is constant, but w, that is dz dt, is not. So the layer has been stretched. Now, potential instability, or potential stability. We've considered already lifting a parcel in an unchanging environment. So static stability asks what happens to parcels of air after a small displacement. Latent stability asks for a large displacement, is there a level of free convection? And so potential stability asks what happens if we lift a whole layer and the environment changes. If the layer is statically stable after lifting, then it's potentially stable, and if it's statically unstable after lifting, then it's potentially unstable. Whole layer lifting happens head of fronts, for example, with large-scale lifting, or large-scale subsidence on the eastern flanks of high-pressure systems. To calculate potential stability, one lifts the entire layer to saturation. And the reason we do this is once both the top and the bottom layer are saturated, they ascend along saturated adiabats and the lapse rate won't change anymore. So what typically happens is that the bottom of the layer will saturate before the top of the layer, and so you need to lift the layer a little bit more before the top of the layer becomes saturated, and that's what's happened in this case. And here we can see that the layer is potentially stable because it's statically stable before lifting, and after lifting it's still statically stable. So there's no potential stability, instability here at all, it's potentially stable. And we notice that for the layer, d by dz of the wet bulb potential temperature is greater than 0. And so that's a condition for potential stability. In the bottom case, the bottom of the layer saturates first, and then the top of the layer after some lifting. We find that the theta sw dz is less than 0. And after lifting, the layer possesses static instability. And so we say that it's potentially unstable because, or contains potential instability because once we lift it to saturation, it now is statically unstable. So you can see how this depends upon the lapse rate of the wet bulb potential temperature. If it's greater than 0, then the layer is potentially stable, and if it's less than 0, then it's potentially unstable or contains potential instability. So the best way to do that then is to calculate the wet bulb temperature profile, and then you can very readily see what the wet bulb potential temperature lapse rate is like. So if we look at the lowest layers of this trace, you can see that there's a region that's potentially unstable because the theta sw dz is less than 0. Then the layer directly above it, the theta sw dz is greater than 0, and so no amount of lifting will release any instability in that layer. For the third layer, the theta SWDZ is approximately equal to 0, so it's neutrally stable. If you lift that layer, both the bottom and the top won't change. The lapse rate won't change at all. The layer above that is potentially unstable because, again, the theta SWDZ is less than 0. And the uppermost layer is stable, potentially stable, because the theta SWDZ is greater than 0. So the way to do that by inspection then is to calculate the wet bulb or the pseudo-wet bulb profile. So here's an exercise for you to perform. Plot this trace and then calculate the wet bulb temperature. Remembering the way in which this is done is go up a dry adiabat and the mixing ratio line from the given pressure till saturation and move back down a saturated adiabat to your original level. So plot this wet bulb temperature trace and then fill in the table for TW and potential stability. Pause the video now and do that exercise. How did you go with that? Here's the result and here's the actual plotted profile. So for the lowest layer it should be neutral stability, potentially unstable for the second layer, and then potentially stable for the next two layers.